Well, welcome all. Today in chemistry, we are going to wrap up our unit on the atom by exploring the average atomic mass on the periodic table. So we're going to kind of look at why you can't really just necessarily use that number rounded when you're talking about the mass. So we're going to kind of talk about that today and figure out where these numbers come from. I just put these on because they're fun pictures. I'm not sure why they're on this presentation. Okay, so take a look at this. So have you ever wondered, why is there a 12.01 with the average atomic mass? And why is there a 39.948 for the average atomic mass? And why are they calling it an average? So we're going to take a look at where this average comes from and why it's related to how many isotopes are present and why it's not always an easy average. So as we look through that, that's what we're going to explore today, is where did these cool numbers, these decimals come from, and how do we use them? Okay, so here's the basis for this. So an isotope is something that has the same atomic number but differing atomic mass. So this is the three isotopes for carbon. So you have carbon 12. So carbon 12 has 6 protons and 6 electrons because they're always equal, and it has 6 neutrons. Okay, carbon 13 would have 6 protons because it's carbon, 6 electrons because they're equal because it's neutral, and then 7 neutrons. And of course, carbon 14 would have 8 neutrons. So these all have the same atomic number, but they have different atomic masses, is what that means. So when you look at this, they have different masses. So how does that fit in with the average atomic mass on this lovely periodic chart above me? So there's a little secret here. So there's two factors. First of all, let me just show you something. So it's an average, first of all. So when I average 12 plus 13 plus 14, if you average all three together, you get 13. But if you look at the chart, the average atomic mass for carbon is not 13. So something else is going on here besides just an average. And so what we're actually doing is something called a weighted average. So a weighted average takes a look at how common something is, or the percent of something, and that is weighted in terms of that. So an example of a weighted average is our grading scale. So 80% of our grading scale is achievement. So if you mess up an achievement assignment, it has a really big effect on your grade. We all know that. But progress or practice is only 20%. So we know that if you miss that, it's not as big a deal because it's only, weighted less. Now in this one, the thing that weighs it is something called percent abundance, or how common something is. So the most common isotope, like 99% of all carbon, is this one. So the mass of carbon should be closest to that one because it's weighted the heaviest. It has the most effect. Okay, so when you're taking into effect of this, you look at which one is most common, and that's how you average it in here. Okay, so let me show you an example of this. So here's an example. So boron has two isotopes, isotope 10 and isotope 11. So both of those are stable, both of those exist. But if you look on the chart, the average atomic mass for boron is 11 or is 10.8 or so. So you automatically know that the 11 one is more common because it's closer to the common one. So the average atomic mass is oftentimes closest to the ones that are the most common, or that have the highest percent abundance. Okay, so you actually can do math with these. And so what I have here is a typical problem that you will face in this unit. So magnesium has 3 natural isotopes. All right, so what you should be able to do is you should be able to take and look and find how many protons it has, how many electrons, how many neutrons, and you should understand what an isotope is and an ion and all those things. But basically what they're saying is that there's 3 flavors or versions of magnesium: magnesium 24, magnesium 25, and magnesium 26. And you can see that overwhelmingly that the most common one is magnesium 24 right here. So that one should have the most weight. And so when we find the average atomic mass, you're going to find it's closer to 24 because that one is weighted the heaviest. So to do this, what you do is you do the mass of each isotope times the percent and then add them up. Add them up. That's right, add them up. Okay, so you're going to take the mass. So in this case, you're going to do 23.985. Now, this is the actual mass of this isotope. So you could do 24 and round it. You just would be further off in your answer. So if they give you the mass, actually use that mass number they give you times the percent. So I'm going to take that times 0.787. Okay, so I'm sure you know this, but percent this is the actual number value of 78%, because basically it's times 100. So 0.787 is this value in number form. All right, so you're going to add that to 24.986 times 0.1013. And then you're going to add that to 25.983 times 0.1117. So you're going to add all these up. So you take the mass times the percent and add them up. Now, thankfully, I have my calculator's on my computer. So I'm going to do 23.985 times 0.787 and hit equals. Okay, and then I'm going to add that to, and I'm going to have to use some parentheses here so that I don't screw this up, 24.986 times 0.1013, close my parentheses, equals. All right, and then I'm going to add this last bit down here. I'm going to add plus 25.983 times 0.1117, close my parentheses, equals. And now if you did this right, you would get 23 or 24.309. So 24.309, which if you take a look on the chart is really, really close to the actual mass of magnesium. You can see it up there. So that's how they came up with that number right over there, that red number on the chart. Okay, so you take the mass times the percent and add them all up. Let's try one more. Okay, let's try one more. So you're going to all do this. I'm going to pass a paper out, and you're going to try this one with your lab partner. So copper has two. I'll probably pause this here. So pause, and then we'll try it. So copper has two isotopes, and those isotopes are 63 and 65. So you're going to figure out what the atomic mass of copper is based off of these two. Okay, so you're going to take the mass times the percent and the mass times the percent for this one. So it's going to look like this, 69.692 times 62.93. Again, that's the mass times the percent plus, so it'd be 0.308 times 64.93. Okay, and then it equals. Okay, so we'll bust the calculator out again. Might as well, right? We got it. So 0.692 times 62.93 equals plus, and I'm going to use parentheses here again, 0.308 times 64.93. Close my parentheses, hit equals, and I get 63.54 with which you would use the unit AMUs, which stands for atomic mass unit. And if you look on the chart, that's really close to what the actual is, and that's how they came up with that number. Now, this one's kind of interesting. So you see how it has two numbers, 63 and 65? So this is kind of an in-between number between those, but it shows that a lot of them are this. So that has a little bit more weight in it, and that's why it's not exactly 63 in this whole thing. Now, a final note is because the answer to these are just the red numbers in the chart, like that's the key. So you make sure you can show the work, right? Mass times percent, add them up. But secondly, oftentimes I'll do is like element X. Instead of it saying copper or instead of it saying like magnesium, it's going to say element X has this isotope mass and this one, and then you have to find it. And so you would look for the one that has the answer at the end, and element X's identity would be copper because this is the one that closest matches it. So when we're doing this kind of stuff, that's typically what it'll look like when you have one of these. Okay, I'm going to close up shop here, and we're going to do a couple practice problems and make sure we're all good. This is it, people. Hopefully this makes sense. This is the last little part of our unit, and our test is coming soon. Take care, all.